Hi and happy Thanksgiving! Sierra here. Today I am going to discuss two presenting cases that illustrate the importance of glucose uptake in understanding disease. First, our first case involves a human patient of unknown age or sex who has unfortunately been diagnosed with a glioblastoma tumor. Glioblastomas are particularly aggressive tumors. They originate from astrocytes being specially shaped glial cells that support neuron synapses in the brain. So our tumors originating from that special glial cell, the astrocyte. The patient's tumor is very clearly depicted in their diagnostic imaging, which you can see right here, small copy of. We can see the tumor as the defined area of hyperintensities, or the brighter coloration here on the MRI scan. The second image illustrates a PET scan where fluorescence was used to identify glucose molecules. So both images display the abnormalities in the same location. We can infer from the images that the increase in fluorescence is likely due to an increase of glucose uptake by the neoplastic tissue making up the glioblastoma. The surrounding and seemingly unaffected brain tissue is slightly less fluoresced, which also implies that the cancerous tissue can take up more glucose. In normal brain tissue, glucose is the primary source of metabolic fuel, and it's transported into cells by glucose transporter proteins. Glucose being a very large molecule, it cannot just enter a cell. Specifically, neurons utilize the GLUT3 protein, while glial cells and the cells that make up the blood barrier utilize GLUT1 protein. And both of these proteins are independent of insulin for uptake. And this is advantageous for brain tissue because brain has to use glucose as a metabolic substrate, so it needs a very swift and immediate access to glucose, and it would be disadvantageous if it had to have another intermediate such as insulin in order to do so. There are other body tissues that are equipped to use a variety of molecules as metabolic substrates, and those body tissues serve to aid glucose homeostasis. And some of those tissues are dependent to insulin, and some of them are what we call sensitive, and some of them are independent to insulin, much like the brain tissue. For example, liver tissue is vital for glucose homeostasis because that organ is responsible for providing more glucose under fasted conditions. So liver actually has to have swift access to any circulating glucose as well, and it takes up its glucose through the GLUT2 receptor, which is also independent of insulin. Now, some of the more dependent tissues, such as skeletal muscle and adipose tissue, these are sources of alternate fuels, much like glycogen or fatty acids. And when they take up glucose in the fed condition, they are sensitive to insulin, and both of those tissues use the GLUT4 receptor. So, bringing it back, knowing that glial cells utilize the GLUT1 receptor to take up glucose. And we see in this patient's glioblastoma tumor that there is an increase compared to normal of glucose. It's likely that our cancerous tissue has an increase in the GLUT1 receptor. So, being that cancer is very broadly described as rapid and unbridled cell division, it would be very advantageous to the tumor to increase its amount of GLUT1 receptor, because if we have an increase in the receptor, we also have an increase in the amount of glucose available, and certainly that degree of cell growth and division is going to have an increase in metabolic need. So, backing up. So GLUT1 expression can actually be a prognostic indicator for patients who have a glioblastoma. So, a tumor that has maybe a closer to normal expression of the GLUT1 would reveal that the growth or the metabolic need or maybe even the size of the tumor hasn't expedited yet. So that would be a little bit better of a prognosis. But higher amounts of GLUT1 would imply a higher need for glucose, more growth, faster growth. And so an increase in GLUT1 is definitely a prognostic indicator for disease such as this. Okay, awesome. So let us now consider our second case. Again, we're going to keep this within the glucose uptake family. So here we have a 5-year-old young male who has a chronic history of fatigue, polyuria, and polydipsia. And he presents with some fatigue and general malaise, so we went ahead and did some blood work. Now, diagnostically, the patient's blood work reveals an abnormally low amount of serum insulin. And that's both at baseline and after induced hyperglycemic condition. So after we induce the fed state and increase that blood glucose. And at first glance, we are likely to suspect some sort of diabetic process. We're looking at insulin, we're looking at glucose. But when we take a peek a little bit deeper into it, we see that diabetes mellitus, or type 2, the more common version of diabetes, is not going to be the culprit of the patient's symptoms. So if we take a look here, let you guys see that, then we see that the insulin levels are abnormally low compared to a control. So control would be normal under both conditions. So this is low insulin. So we might expect with type 2 diabetes that while that glucose remains high, okay, because it's not going anywhere, that insulin might be high as well, or normal. It just would not be a low amount of insulin because it's there. It's just not able to help tissue utilize that glucose. The patient has become resistant. So that's clearly not what's happening in this particular case. So instead we have to look at a different characteristic of why this insulin is not available, and this could be revealed by type 1 diabetes. So type 1 diabetes is characterized by insulin resistance in tissues, and it is an autoimmune process. So it's also referred to as juvenile diabetes. So this also fits with the presentation of our patient because it is young people who are typically found with this disease because they are symptomatic for quite some time. That's a genetic disease. So we usually find that diagnosis pretty early on in their life. So this patient is experiencing low insulin serum levels, even with hyperglycemia. So if we are to assume juvenile diabetes, which is also characterized by polydipsia, polyuria, fatigue. So what could possibly be happening in juvenile diabetes is that for some reason the autoimmune mechanisms are attacking the islet cells of the pancreas. So the cells that create insulin, the body is actually attacking those cells. So they are not secreting enough insulin because they are under attack. And if there is no insulin circulating, then we have very poor glucose uptake because that hormone has to be there for receptors like GLUT4 in order for that glucose to be taken in. So the lack of glucose uptake would lead to hyperglycemia under fasted conditions, much like in type 2. So the glucose is not getting into the cells, so the circulating glucose is going to be high. And the increased osmolarity issues can explain the polyuria and polydipsia. So, so even though glucose is circulating in the individual, and you can see that, okay, so hyperglycemia in the blood, it is circulating. The lack of uptake does mean that we have a perceived fasted state. And it's a false fasted state, but the body and what it's actually using for its fuel, it is assuming a fasted state because glucose is not actually getting into the tissues. So this means that glucose homeostasis has to be triggered, and gluconeogenic pathways are active and elevated. So our two main glucogenetic pathways are glycolysis and glucogenesis. And it's likely that glycogenolysis, so our main glutogenic pathways are glycogenolysis and glucogenesis. And it's likely that glycogenolysis, so glycogen being a storage molecule that helps with glucose homeostasis through breakdown, it's likely that enzymes of this are elevated. An enzyme of that sort could be glycogen phosphorylase, which aids with the breakdown of that storage. Because these processes occur simultaneously in the body. However, this is a chronic disease, and this patient has been experiencing a chronic condition of this perceived fasted state by the body. The glucose has not gotten into the cells for a prolonged period of time. Again, this is a genetic disease. So if that's the case, we're not looking at a short fast period. We're looking at what's an elongated fasting period or even into starvation perceived by the body. So it's most likely that enzymes of gluconeogenesis and even ketone body synthesis are elevated. So in extreme cases, the body will produce ketone bodies as a means of metabolic fuel, and this can and is not preferred. Remember our discussion about brain tissue. It is not preferred, but it can be used by the brain in lieu of glucose as an energetic source. Now, under prolonged periods of the use of ketone bodies, the breakdown and use of them can cause metabolic acidosis. So this is definitely not what we want to see in this patient. And occasionally, in extreme cases, juvenile diabetes does lead to metabolic acidosis. So we might assume that the enzyme specific to gluconeogenesis, the pathway that reverses glycolysis so that we can get that glucose molecule, other than dietary means. Enzymes like pyruvate carboxylase are important for reversing that glycolysis, but if we remember, glycolysis has three main regulatory steps that are irreversible. You cannot go backwards. Those reactions are one way. And so we have to find a way around those, and pyruvate carboxylase is a way that we can get around a regulatory step and start backing up that pathway. So enzymes like pyruvate carboxylase may be increased in this patient because of the degree of gluconeogenesis, because the body assumes that there is no glucose for use when it is there. So if we are to assume that this patient is also in this prolonged fasted state, and now we are ketogenic, levels of ketogenic enzymes like acetoacetate decarboxylase would also be elevated in this chronic disease. And so this could be a way that we determine the severity of the metabolic state of our patient. Perhaps we haven't made it to a ketogenic period and we're just looking at the enzymes of gluconeogenesis. But if we do have that elevation of ketones or ketogenic enzymes, then we need to intervene pretty quickly to help this patient in their metabolic state. So luckily, with treatment, insulin supplementation and a good diet, most juvenile diabetics can be managed and have a great have a good prognosis. All right, so this illustrates two reasons why glucose uptake into the cells is an extremely important component of metabolism of modern medicine, and there are so many avenues of disease and drugs. So this is a very important concept, and we've explained that in two ways today. So thank you for joining me today.